Welcome back, Earth scientists. It's time to learn about landscapes and geomorphology. Take a look at that landscape, right? It's pretty awesome. That's Mount Rainier in Washington State. But there's so much more than just a pretty mountain there. A lot of clues gives us insight into what created this mountain, what it really is, what it used to be, what it could be again in the current tense or future. So this lesson's all about learning about landscapes, what they kind of represent to Earth scientists, to look for certain clues that help us understand why they're there, and if their presence indeed tells us about an event that caused them to be made, what that special event was. So we can't be talking about geomorphology without talking about the scientific discipline itself. When Earth scientists look at landforms, we call that geomorphology. So let's kind of break that word apart. Geo for geology and geography. Geography being the study of where things are located, geology being the study of rocks, fossils, minerals, so forth, landscapes. But more importantly, geomorphology takes a look at the processes by which shape them. And I'm going to give you an example of an experience I had in grad school on one of the many field trip related things you have to do in geology, where they take you away for like a weekend or a week and you go travel. And one of our projects was to go travel somewhere with someone in your class and try to figure out how it got formed. So I was traveling with this person and we're driving through Nebraska, and shockingly, we came across some incredible geomorphology that I was like, man, I am certain that the very tail end or terminus of the last ice age ice sheets, known as the Pleistocene epoch, this stuff was carved by that. So we pulled over at the next big city because we were really in a remote area, stopped and got a geology roadside book, which they make for many states, not all, but they certainly had one for Nebraska. And we confirmed our hypothesis based on what we had seen and how we knew thus far by looking at maps, having visited other places, learning how they formed. That's a real-life application of geomorphology. So we're going to learn about a number of different landforms, and then we'll even go a step further for certain landforms, and plains are one of them. We'll be looking at specific types. So you could imagine a plain, quote unquote, is a flat area, right? But there are different types of plains, and there are those that are along coastlines. There are those that are in the interior portions of continents. Coastal plains are relatively flat. They're adjacent to coastlines because not all coastal areas are flat. There are many areas that are extremely rugged terrain or mountainous, and there's reasons for that, geologically speaking. But whenever you have coastal plains, you'll have things like low rolling hills, flat topography for the most part, even basins being indentions in the ground that can fill up with water, such as swamps and marshes. So they're like terrestrial transitional areas where oceans, seaways meet land. So these coastal areas are very important. So here's a coastal plain in Oregon, right along the main highway that goes along the coast there. And you can see just rolling hills. There isn't any mountainous topography right there, but you can definitely see for the most part it's flat, minus the sand dunes that have kind of been anchored down by vegetation. Interior plains are different. These are landscapes that are relatively flat in comparison to maybe what's around them. And they are in the interior of continents, meaning interior away from coastlines. They're in the middle. In this particular case, I am flying over a part of the South Island of New Zealand, and it was noticeable because there were mountains on either side, and then there was this big plain area, flat area in the bottom, which happened to be an outwash plain from a glacier. And what you're looking at is just all this water down here. This is sediment that's been deposited by some melting glaciers in the neighborhood. So interior plains come in a lot of different shapes, fashions, and forms, but they're typically characterized by trees, by grasses, where your coastal areas may be sand dunes, or they could be other types of vegetation found in that area. Interior plains can also be desert environments like this one. This is a place in Arizona, and you can just see the rolling hill topography. It's fairly flat for the most part with a few hills there, but not mountainous, and we'll define a mountain shortly. The next landscape that I think is super important to distinguish from some of the other types of features you'll learn about in just a second is what a plateau is and is not. I can remember one year on the geology field course, one of my counterparts, meaning another instructor who was teaching the backpacking and camping, looked over to me and she goes, "You know, what's a plateau?" She was being serious. This is somebody very well educated. She goes, I'm confused. How is it different from a mesa? How is it different from a butte? What is it? I was like, well, that's a great question because it's not as simple as it sounds, but plateaus are typically regional in scope. They are areas where land has been as generally horizontally deposited sedimentary strata. It could be some lava flows. They're pushed upwards. And so that whole geographic regional area has been pushed up, but not as a mountain. Those are plateaus. So they're big scale regional. For something like a mesa that we'll get to in just a moment, they're very localized. Plateaus distinguishably are going to look higher than the rest of the land around them. Oftentimes, plateaus are carved out by some type of current or ancient type of water, wind, or ice type situation. Case in point is the Grand Canyon, which you're seeing right here. And looking at the Grand Canyon, you can see there's a big hole in the ground, right? That hole got there because the Colorado River started carving down these rock layers, the sedimentary strata, and then got down to the basement rock, which is the stuff that used to be a big giant mountain. That's the oldest rock at the bottom. So think plateaus as regional geographic areas, not just a localized flat place, okay, that's been risen up. It is noticeably regional, huge. There's a place in Texas called the Edwards Plateau. This area is also referred to as the hill country. The hill country does have hills, but it doesn't have mountains. And the whole geographic region has had some uplift, which gives that beautiful scenery that people think of when they think of wildflower season in Texas. That's a plateau region known as the Edwards Plateau. Even in places like Australia, there are coastal plateaus like this one, where there's just these big giant rock formations that tower up from the land, and they are regional. They're not just a localized peninsula like this shot makes it look like. The peninsula is huge. In fact, Sydney, Australia, sits on this entire rock formation. It's a very large plateau area. Getting back to the Colorado Plateau, which is where the Grand Canyon and other areas in that situation exist. So Colorado Plateau includes portions of New Mexico, Arizona, Colorado, and Utah. This land was buried under thousands of feet of sediment. The Grand Canyon is grand because it got carved out so fast, and we have such a great rock record, but it's not complete. And it's an example, if you fly over it and you look down, it is shocking how big it really is. And you begin to see its scope when you look out an airplane window, however you're traveling in the sky, and you look down and see the ground beneath you. You can see how it's raised up on a regional perspective as compared to everything else in the area. That brings me to a couple of other landforms that are similar to plateaus, or in the same family, should I say, but those are mesas. This is in Canyonlands National Park, which is in Utah, and you can see how they're tabletop. They're very localized features, so they're pretty steep, right where they're located, and pretty flat. That's pretty much the definition of a mesa. They are not regional. While there's a lot of mesas in Mesalands National Park, it's and it is part of the Colorado Plateau. Don't mistake this as being a plateau because it is a small topographic feature in comparison to what we would think of as a plateau. The key things, they're flat top and they have very steep slopes. They're usually, in my opinion, wider than what the next feature is we'll look at, called buttes. So buttes, I kind of chuckle sometimes when students look this up because they'll say, well, it's like a mesa. Kind of. It kind of is. But it's not, because it could have been a mesa in the past, but a butte is very steep and it has an irregular or bumpy top. So where does that come from? You're like, well, that doesn't look so bumpy. It is. It's very different from what a mesa's tabletop like. Buttes can have all different shapes at the top, and they're usually narrower. And in my opinion, I've seen many of them that tend to be steeper than just your average mesa, but don't underestimate the steepness of any mesa. So there's 3 very large mesa systems in Arizona that are referred to as Mesa 1, 2, and 3. And those things are insanely steep. And because of them, it's important to note that there wasn't a really good source of water for the indigenous people that lived there and still do today. So they, in many cases, had to find a way to get water and bring it up to where they lived on the top of these remarkable structures. So keep in mind that buttes are like mesas in that they're smaller features, very steep with an irregular or bumpy top. How does that happen? It happens from something called differential weathering, and that is created by a rock's hardness based on not just the minerals it contains, but how well the rock grains are cemented together. You get a piece of sandstone, and it may have one section of it that weathers faster than another. It could be how water touches that rock, and so water may impact one section where it doesn't another. Or let's say you have a sandstone layer, and beneath it you have a limestone layer, and above it you have a shale layer, which is like mudstone. Well, the shale is softer than the sandstone, so it would have something called a higher differential weathering capacity, meaning it weathers faster than something with a lower differential weathering capacity, low for slow, high for fast. Buttes haven't weathered completely away, so they must have some type of low differential weathering capacity, at least for the rocks towards the top. Looking at this place, this is one of my favorite locations in Sedona. Look at the shape of that rock. See the irregular, bumpy top to it. So let's compare mesas to buttes. Do you see a difference? So to say a mesa and a butte are the same, it's not true, because buttes are very distinctively bumpy and irregular, while mesas are flat-topped. You will find a number of these structures, especially out west. My personal favorite landform is called a hoodoo, and that's what you're looking at here. So hoodoos are spires. First of all, spires are rocks that are kind of in this kind of fashion. But what makes them special is they have a knob on top, something that's hard that anchors that rock in place, referred to as a cap rock. If you don't have that cap rock, that spire is going to disintegrate quickly in time frame, even human reference. So this is in Bryce Canyon National Park in Utah, and there's a place right outside of Bryce called Tropic Ditch. And for the last 2 decades, every year that I've been out there, I've been documenting the same set of hoodoos and spires with photography. And we would show this on our field course where we'd show students, okay, well, here's what it looked like the last few years. Here's what you're seeing today. And then one year we went and the spires were gone. That's a human reference time frame. So without a cap rock, these types of softer rocks can weather very, very quickly. So there are very few places in the world that are conducive to forming hoodoos. There's a few of them even in another place in Utah that is called Goblin Valley, but they don't look at anything like the ones you see here in Bryce Canyon. This is the highest concentrations of hoodoos in the world. You typically need a high elevation to do it because these rocks form, if you can see this land right here, it looks like it's just a piece of almost a fin of a fish, but it's just a block of rock and it's slowly fracturing and weathering because of something called frost wedging. Most of the nights of the year are high enough an elevation to produce a freezing situation. And so when water and snow get into these fractures in the rock, they bust them apart and they create these phenomenal structures known as hoodoos. Look at the left versus the right image, and you can see the difference of a spire versus hoodoos, and they're just noticeably different. So spires aren't going to last very long. I'm not going to say that hoodoos will last indefinitely, because they won't, because once that caprock wears off, the whole thing will disintegrate in pretty rapid geologic time. So understand the difference between the two, because spires, while they're in the definition of a hoodoo, they are not a hoodoo. Hoodoos have to have the caprock. That's another amphitheater shot from the rim looking down into this at Bryce Canyon, and they're extraordinary, aren't they? They truly are. And you can hike down into these if the trails are open. And while they look little here, they are not. They're enormous. And you get on them, you're like, wow, they're huge. And you just look up and it's almost unthinkable just what they are and how they operate. Another landform that you will likely see, especially if you go out west, but it's not the only place you will see it, are arches, which are natural arches, rock arches. The highest concentrations of arches, to my knowledge, in the world is in Arches National Park, and that's found in Utah. There's a lot of great national parks there. But typically what happens is, if you notice, this is Delicate Arch, which is one of the most famous arches in the world in that national park. This rock formation matches that behind it, and there's air between the two. So you might go, well, running water caused this. Not necessarily. It could be a good hypothesis, but what we can see is that slow weathering processes, things like frost wedging, chemical, other types of mechanical weathering, and some wind action probably helped weather and erode the connecting rock between these two areas. And over time, this disintegrated right here, leaving behind an arch. Over time, you could lose the middle of this, and it'll likely topple over, not even graduate to hoodoo status, because it's just not going to be strong enough to hold up that amount of weight. Arches come in a lot of different shapes in a lot of different places. This is in New Mexico at a national monument. And you can see that natural arch. Well, you can also see a lot of rocks down here. So the arch will give way over time. Photograph them while you can, because arches are special and they don't have a huge indefinite life cycle in the geology realm of rocks. I want to talk about slot canyons because I personally love them, but I get a question about these a lot from students because they start looking online and they begin to see a place like this. This is Antelope Canyon, specifically Lower Antelope. There's an upper and a lower, and it's right outside of Page, Arizona. And you look at this, that sandstone's the same on both sides of the wall. While you see the lines in the rock, I don't want you to be deceived that those are strictly because of whirling water. While that slot canyon was formed by whirling water from a flash flood, you're seeing cross-bedding in the rock, which cross-bedding are where ancient sand dunes develop their sand layers, and it makes a crisscross format. But these slot canyons can be extremely dangerous because if you're trapped in one, and water rises unexpectedly because it may be raining somewhere upstream, not where you are, it can flash flood in a moment's notice and you can't get to safety. So always think about checking the weather of where you're going if you're hiking in remote places and you're seeing something like this. While they're beautiful, there's always that sense of paying attention to the potential danger. This is another slot canyon, and it's in Utah. Not in Arizona. This one's actually in Zion National Park, and this is the Narrows. The Narrows is a really famous place in the national park, and sometimes you can actually hike it if the water flow is not too fast and the park has it open. It's that same geologic formation you saw at that other slot canyon. There are people who have died because of flash flooding. So I can't emphasize enough how important it is to recognize when you see beautiful things like slot canyons, there always is a risk associated with them. Another type of landform that you will see, especially if you travel out west, is something called Badlands topography. There is a place called Badlands National Park, and that's in South Dakota. But this place that you're looking at is actually in the middle of Arizona, in between Flagstaff and the turnoff to the south rim of the Grand Canyon. Badlands is simply a term applied to barren landscapes that don't support much vegetation. And those hills might look kind of soft, and they, in retrospect, kind of are, but they also have material that kind of keeps them together. Eventually they'll weather apart, but it's not like a sand dune. And I don't want you to get that opinion, but they're not stable either. This is another example of Badlands topography. This one's actually in Nebraska, of all places. This is Toadstool Geologic Site. I kid you not, that's its name. Toadstool, and it's because they're little, almost mushroom-shaped features that are very similar to hoodoos. They're just unique to this area. But this is that type of almost no vegetation up there on those rocks, and so it's quite barren. This is a description that geologists and our scientists refer to as Badlands topography. This is that toadstool site I was talking about, and you can see that it's just kind of sticks up random in the middle of nowhere. If you went off the grid for a week or two, this would be a great place to go because it is really in the middle of rural Nebraska, almost to South Dakota. I was just surprised when we got there how many people were living that way and camping out at this location. But when we did the hikes and got into this area, it was really spectacular. So moving away from some of these landforms you've learned about already, we're going to graduate into bigger items, such as mountains. So while this may seem obvious, mountains have to have a certain immediate topography change from the surrounding landscape to qualify, and that magic number is 1,000 feet. If you don't hit that magic number, it's not going to be a mountain. It's a really big hill. Okay. Typically, mountains also have some type of summit. They have, not always, because they could be older, what I would call senior type of mountains. For example, the Smoky Mountains along the Appalachian Trail. They're more senior. They've been around for hundreds of millions of years, have had more time to become rounded. Where you go somewhere like the Rocky Mountains, they're very jagged because they're much newer geologically speaking. So there's a variety of types of mountains, and we're going to learn about 4 different types. We're going to start with folded mountains. Folded mountains means there's been some type of plate collision, and when that happened and the 2 plates collided, somewhere beneath the Earth's surface where it was hotter and the rocks were more malleable and pliable, they got deformed. So rock deformation is what we call that. When rocks are deformed, they take on special shapes, and they're called rock folds, geologic folds. They're going to be anticlines, synclines, and monoclines. Guaranteed question for assessments. All folded mountains are caused by compression. All of them. So things smash together, not by being pulled apart. That's not what creates the folding. So we're going to learn about the 3 types of folds. There's monoclines, synclines, and anticlines. So let's talk about monoclines first, the root prefix being mono for 1. You can see the flexing right here. This is actually in the Colorado National Monument, and you can see where it's folding just on one side but doesn't come around the other side. So when it folds in one direction like that, it's referred to as a monocline. You can see this is a monocline out near Ruidoso, New Mexico. I took this shot. I was like, pull over. This is a great monocline. And you could see that it was just being bent in one direction. So when you see a syncline, I want you to visualize a smiley face looking right back at you like I put on the rocks there. That's how you're going to know. Sometimes I've actually seen these things painted on rocks. Please don't do that. And if you're around people who do, please tell them not to. That's defacing rock formations. That's not okay. But you think about this, it's a concave shape. So big smile and put little eyes on it, imaginary eyes, and it smiles back on you. It is a syncline by definition. Here's a great syncline. You look at this one in Chile, and you can see that concave look. So just make imaginary eyes looking back at you, and you got a syncline. The anticline is like a rainbow. So it's a fold that has an arch. So A for arch, and it's convex in shape. These are my personal favorite of the folds. I just like the way they look. I like them all, actually, but for whatever reason, I am fascinated by anticlines. But anticlines or synclines or monoclines are evidence that we've had some type of folding episode in plate collisions in geologic past. Here's another anticline right here, and you can see some geologists working on an anticline right there. Let's move into the next type of mountain known as a dome mountain. So sometimes students want to marry this up with volcanic mountains. I'm not saying that you wouldn't form domes in volcanic areas, because you can. But domes are distinguishable by the types of rocks that make them up. And what you're looking at, this is Needles Highway in South Dakota. So it's part of Custer State Park. It's a beautiful area. This whole region got uplifted to create the Black Hills. So that's a really famous place for a number of reasons. One is for motorcycles for the annual Sturgis Rally right around the beginning of August, and then primarily from this remarkable geologic feature. So what you had is a magma chamber, and either it got uplifted or caused the uplift, and or the rocks on top of it have weathered away. And both types of situations have occurred right here in South Dakota. So dome mountains are typically have their roots, the insides of them, made of igneous and or metamorphic rock instead of sedimentary. And that's important because there are things like granite or gneiss, which is a metamorphic type of rock, but granite's igneous. Here's a shot of that same area, and it's my favorite part in Custer State Park, known as Sylvan Lake. That rock formation is nothing but intrusive granite. And so it's the Black Hills is big, one giant dome, and the region was pushed up almost like a plateau, but it's not a plateau. It is distinguishably a mountainous region. So we looked at folded mountains. We've looked at dome mountains. We're going to look at fault block mountains now. What does that really mean? So if you could imagine that one hand represents a big portion of a mountain, and here's another, same mountain, and then one section falls or one section is pushed up, big blocks, big sections of that, aka the Rocky Mountains. So if you've been to Colorado, you have seen this if you've been to Rocky Mountain National Park, which is what you're looking at right here. Huge blocks of rocks have been faulted and displaced, and that gives a very rugged terrain and makes for a very complex structural type of situation for the geology in the area. This is another shot of the Rockies. You can almost see those fault blocks sitting side by side on the Rocky Mountain range there. And that's how the Rocky Mountains are arranged. And one reason that you see ski resorts in different parts of the fault block mountains is because they're at different elevations and the blocks have been shifted at different places and they're conducive to that type of situation. Here's another fault block mountain, and this one is a great place to visit. This one is the Grand Teton National Park in Wyoming. This is a very iconic view. So you get a plain area down here at the bottom, and then just these just gorgeous mountains that just tower above everything. Now they get their really distinctive shape because they were carved out by the last ice age. So they're horns, they're glacial horns. But these have definitely, they're big fault systems that have caused these sections to be made the way that they are. And if you ever hike into this area, you can see the fault systems when you're in the region. That brings us into the next major landform type, and that is volcanic mountains. So this is the fourth group of mountains, and then we're going to look at three what I call volcano body plans. So volcanoes are not all alike. In fact, if you get into a specialized majors course, you would learn probably then more than three major body plans, but these are the three big ones that I'm going to talk about today. Volcanic mountains have to originate from volcanism. That may sound obvious, but what do I mean by that? Not only is there a magma chamber like we can get with the dome mountains that you learned about earlier, there is a volcano mountain that forms at the surface above the ground. There's three ways that can occur, and sometimes they can occur in more than one way, meaning you can see more than one type in an area. So there's a place in Northern California referred to as Lassen Volcanic Field. It's a national monument. It's extraordinary. It has every type of volcano body plan and then some, not to mention thermal features. They have mud pots, fumaroles, hot springs, things like that. So really, really cool things. So we're going to take a look at each type of volcano body plan, starting with shield. These resemble like a big rounded shield. This is Mauna Loa in the island of Hawaii. And if you're going to fly into either Kona or Hilo, and you're going to have to cross over this somewhere. And yes, that's snow at the top. It's almost hard to believe, but shield volcanoes are monster huge. While their elevation above sea level may be low, their total relief from their summit down to the bottom of the ocean floor where they began to grow, one layer at a time, makes them the largest structures on Earth. I mean, we're talking much bigger than Mount Everest. These things are enormous. So you have to think about the complexity of them. And since they grow up rapidly in geology age, a shield volcano like Mauna Loa is hundreds of thousands of years old, no more than 1 million. So we're looking at very young, geologically speaking, to get that huge. That's consistent volcanism. Now, on shield volcanoes, I need to disclose it's very common to see the next body plan that we'll get into called cinder cones. And cinder cones are little bitty, what you probably would have drawn. If I just would have asked you to draw a volcano, that's probably what you would have drawn. But let me give you one more tidbit about shield volcanoes. Because of the type of magmatic material they have in their magma chambers, most of these are not highly explosive. In fact, they usually produce the least explosive of any type of eruption. Certainly the plumbing and the mixing of magma could change the chemistry, which will change how they explode or erupt. But most of them are very, very not as dangerous as the ones I'm fixing to cover. Cinder cones are the simplest body plan that we have for volcanoes. And here's why. There's one magma chamber, one conduit. So magma chamber, one conduit, volcano on top of it. So it's not going to typically blow out the side. It's not going to typically create what we call a lateral eruption, pyroclastic. You may have some pyroclastic material, which you can in a cinder cone. This area certainly did. This is a Mauna Kea in Hawaii. But the volcanic pipe has to be attached to just one magma chamber. In other words, you don't have a lot of things coming off like dikes and sills and what we call laccoliths. These are features that are intrusive, or more than one magma chamber that feeds it. So if indeed you do, you're going to have the last body plan, which is by far the most violent. These can be pretty violent, but they're pretty short-lived, geologically speaking, unlike where we might see something like shield volcanoes, which are hundreds of thousands of years, where they're repetitiously erupting. These may just erupt for several months or 100 years and then stop. Here's another cinder cone volcano in Hawaii, and these are all over a big giant shield volcano. So I do think it's important for you to know that you can get these things joining up together. So the big dogs of all of the volcanoes, the most dangerous ones, are called composite, also referred to as stratovolcano. I prefer the word composite because it's more descriptive of what they are. Yes, you've had a series of eruptions that made these steep, rugged summits. So they are taller in elevation than cinder cones or shield. They typically bear glacier fields. And the key thing that's important about them is they have multiple conduit systems attached to a magma chamber. So there's lots of ways for these things to erupt. For example, it could erupt out the side here, creating a lateral eruption. It could erupt right out the top, like we think most eruptions do. It could have a dike that brings a whole system of material out this way. So there's a lot of different complexities about composite volcanoes, making them extremely dangerous. This is Mount St. Helens in Washington State. So you have to imagine it looked just like the other volcano back in 1980 in May, the morning that it erupted. And then now it looks like this because in a matter of about 10 or 15 minutes, it lost a third of its vertical elevation because it blew out the side in a massive eruption, pyroclastic eruption, and caused massive widespread devastation. So this is what's left. and it knocked out an entire old growth forest. They're replanting in the area, and then you can see all this is ash. It's the pyroclastic ash and the lahar, which are deposits of mud flow from a volcano, which you'll learn about in the next lesson. Another landform I think is important to talk about, especially if we're looking at something like a composite volcano and even domes. Mountains are calderas. Calderas are always associated with volcanoes, but explosive ones. So what happens is you get a volcano, you get a very quick ejection of material, like most of its magma chamber contents, and there's not enough in it to keep the weight of the rocks from collapsing in on itself. So literally the whole thing goes and collapses down. This can be a very violent event. If it's in an ocean, it can lead to massive tsunami formations. Some calderas have water, and I will show you one in just a minute that does, and they're very beautiful for the most part, but I wanted you to see that they're fairly circular in shape. They're regional, so what most people think calderas are just, little bitty. They're not. They're huge. Sometimes you got to get up in the air to see the indentation in the ground. And then you can go, oh man, that's a clue. That's a clue there used to be some kind of really violent volcano in the neighborhood. So another famous place that is made up of calderas is Yellowstone National Park. Now, Yellowstone is part of the Yellowstone caldera. There's two others. One's even bigger than the Yellowstone caldera. And they came from these just incredibly huge, the largest types of volcanic eruptions that humans can classify. And very recently in geologic time, I might add. So Yellowstone, when you're there, you can see the whole system looks like it's fairly flat for portions of it. Then it has a ring around the outside, and that's kind of where the higher points of it are. You're in a caldera system when that happens. So this is the magma chamber. In the case of Yellowstone, the magma chamber is fairly shallow, and geologists think that many of our calderas had shallower magma systems than something like we might see in Hawaii. So that's why you don't see as many of them in a place like there. This is Crater Lake in Oregon, probably the prettiest caldera system that most people think of. It is a beautiful place to visit. This is an active volcano, by the way. People might say it's dormant, but this is called Wizard Island. So if you took the water away, it would have grown off the bottom of the floor of the caldera. So I see that's scary to me because that means that we've had resurgence of a caldera. That's always a clue. So I get questions often, well, could this thing create a tsunami if it had like a landslide or something like that? Absolutely, it could. So we've learned about the different types of mountains. We've learned about the different types of volcanoes and various landforms. We're going to take a step back and look at how do we interpret those. We interpret them on maps. Maps are used by scientists to help us bring to scale in a human reference things that are huge. So they allow us to show landscapes in a proportional size, usually on paper. And so if we had to put a mountain on a paper that was the size of a mountain, we couldn't create paper that big. So we scale things down and we use different types of maps in geomorphology in order to interpret landscapes that we may see. How could this benefit you? I think it's important to note that, let's say you travel or you hike. Knowing elevation changes, knowing landscapes, knowing if you're in a basin, if you're in something like an area where there's a big plateau, that could change the equipment you might need. In military, this is absolutely an imperative thing to know, is you're using maps to know exactly not just where you're going, but what does the terrain look like? What are your barriers? What are the things that you need to plan for? So on a map, all we're doing is transferring information, big scale, and putting points and lines together that help us narrow down and interpret what we're seeing on a much more human, relatable scale. Which brings me to legends and scales of maps. So what is a map legend? In a map, it tells you the symbols that are used on it. So it would tell you what all of these lines are. It would tell you what these numbers mean. It would tell you its scale. So a map scale means that it has a unit of increment, which is usually an inch on a map. So 1 would be the inch, and then you see the colon to 100. So let's say your unit was 100 feet. 1 inch on the map equals 100 feet on the ground. So the smaller that number is, the second number after the colon, the more zoomed in the area is. When you're seeing a big regional area, the bigger that number is going to be. So we'll take a look at several of these types of maps and show you some of the pros and cons to different types, but they all have a purpose. There's a lot of different types of mapping out there, but our scientists use a variety of these for different purposes, different reasons. And we don't just use them only on Earth. We have mapping techniques that we also use in outer space. So the Earth is divided into imaginary lines. And other planets, respectively, could be as well. So we have an equator, we have poles. So those are the ones that go around from east to west. Those are called latitude. Longitude are poles to poles. So they go from here, from the north to the south. They are long ways. So both play a really important role in X marks the spot wherever a point is on the planet. I do want to point out that there's a place called the prime meridian, which is 0 degrees, just like we have a 0 degrees for the equator for longitude. That's in Greenwich, England. So if you're way out there on that part that's the international date line, FYI. So if you cross the international date line, if you're coming from America, let's say you're going to New Zealand and you cross the international date line, you're going to be in a different place and a different day in particular. Subsequently, when you travel the opposite direction, you'll be in another time zone. So we have 24 time zones on the planet. Be interesting fact, how many do we have in the United States? So time zones are important to how, here's your Greenwich meridian, by the way, going right through here, as we were talking about just a second ago. And this is the 0 longitude, and then you get your equator, which is the 0 latitude. But our time zones are only related to longitude, and essentially they cover 15 degrees of the 360-degree circle or sphere that our Earth makes. So they're little slices, if you want to call them that. And each slice is a time zone. So each time zone, important to know where you are on the planet, what time it is. So you probably, if you haven't traveled, you will run into this if you start crossing into different areas and different time zones. That leads us to another couple of maps that are called projection maps. And projection maps are how we are projecting the surface of the Earth onto the map itself. The Mercator maps are unique in that they are cylinder type maps that allow the current shape of what we know continents to look like. And what's happened is we're using basic longitude this way, up and down, to show between 85 degrees south and 85 degrees north latitude on this particular map. Unfortunately, if you look at how distorted it gets towards the poles down here where the latitude lines are, do you notice starting at the equator, they look fairly normal and then you get a bigger separation? Any type of these projector maps or projection maps will have some kind of distortion. And you need to know that if you're interpreting a map. But these do play a vitally important role of letting us see zoomed in areas holistically so we can understand how they would look for the shape of continents. That brings us to conic maps. And there's a variety of types of conic maps, but this is the just general Lambert type of conic map. And this one illustrates points on a globe based on if you were to make this wrap around, it would join up and look like a little cone, ice cream cone or a snow cone inverted. But you're looking at from the North or South Pole and specifically to a certain degree latitude belt range, and you're looking at those land masses from the polar regions outward. These are used a lot when we're looking at certain types of roads or certain types of zoomed in areas, especially the closer you get to polar regions. But again, there's some distortion, just like you would see in your other types of maps. Now, this type of map is not distorted because it is a very small area. This is a geology map. It's also a topographic map. It's both. But we'll talk about topographic in just a second. What I want to focus in on is the color. So I took the Waco West map, which is a quadrangle that USGS has mapped out number of quadrangles across the world, certainly in the United States, by rock layers that are exposed at the surface. And that's certainly the case for what a geology map is trying to illustrate. It gives you reference to the geologic age. For example, Q refers to the most recent geologic period known as the Quaternary. K refers to the Cretaceous time period when, like, T-Rex lived. So we have a lot of Q and K rocks. They are not in sequence of the geologic time scale. So we're missing some stuff in between. That's important. But what this is, if I was to look for the college, it would be right over here. If you're familiar with Lake Waco, this map's very old, by the way. And this is your map legends. It tells you it was made in the 60s. So the dam is here. And this would be the small river that goes right by McLennan Community College and then hooks and converges as a confluence with the Brazos River. So all of these rock colors that you see here correspond, like this color right here is KAU, that's the Austin Chalk. That would be the geologic formation exposed where MCC campus is located, McLennan Community College. If you get along Lakeshore Drive going by Lake Waco, it's very hilly out there. So that's important to understanding these lines that you see on this map, which will be the next type of map we look at, which are called topographic maps. My point is that geology maps show you what's exposed at the surface. So if you're wanting to go look for certain fossils, certain rock types that we know are certain ages geologically, you need one of these. So topographic maps use contour lines. Contour lines, by definition, never cross. They're the same elevation. Let's say you have a contour line of a 500 feet. That entire line is all 500 feet. Let's say the next line above it's 550 feet. That would mean your contour interval is 50 feet. You have to go to your map legend to find that out. So when you have really close together contour lines like you do here, that means you have steep topography. When you have them far apart, so going back to my geology map here, they're far apart over here by Steinbeck Bend. So the Mammoth National Monument's over here. Here's MCC campus. They're far away over here. That's going to be flatter topography, and this is going to be very steep topography. And if you hike throughout Cameron Park, you know it's very steep. So every so often on a contour map, you'll get a darkened line and there'll be a number that gives you a reference point. So it's an easy visual for you to see, like if it was a 50-foot contour, it'd be 500, 550, 600, 650. Every fifth contour line is darkened for you to be able to reference that. And that's called a contour interval or an index contour. So going back to that scale of the map, it matters. If I was going to look at something like Mount Rainier, which I just showed you on the prior map, if I had a 1 to 250,000 scale map, that would tell me that 1 inch on this map equals 250,000 inches on the ground. If I have 1 to 24,000, that means 1 inch on this map equals 24,000 inches on the ground. How does that translate into real live use of maps? The smaller the second number, the more zoomed in the area is. Okay, so the further away it is, the larger that number is, meaning 250,000, it's more zoomed out. You have a bigger regional area that you're seeing. So let's apply what you've learned and what you know. So you go take a trip here. You take this class and you're like, I'm gonna go. Even if you've been, you're like, I'm going back. I know a lot more about the Grand Canyon. Now you know it's a plateau. You also know that there's some clues just by how it was made and what we're seeing that tell us about its history. Knowing this information can be valuable. So if you've spent any time out in Arizona, you know that it's arid out there. And I will tell you that the plateau, depending on where you are on the Colorado Plateau, you can get as high as over 9,000 feet at the North Rim, for example, of the Grand Canyon. That's important because you're going to need to know these things. Using a topographic map could be important so you're prepared for enough food, enough water, whatever hiking materials, camping materials, permits that you might need. These are real life applications of applying knowledge about landscapes and geomorphology. You decide you're going to go visit somewhere like Toadstool geologic site, better go prepared because it's out in that part of Nebraska, northern Nebraska, and it is dry, dry, dry. It's in the plains, the Midwest. It's what we call the Midwest, but yet we have a Badlands topography. You get stuck out here, let's say 150 years ago, it could have been a death sentence if you didn't have a way to get water. So it's super important to know your landscapes, know the kinds of environments that are associated with them, and how you need to prepare yourself when you're visiting them. If you go to a place like this in Colorado, this is on the road that goes in and out of Estes Park to the Rocky Mountain National Park, these rock layers have not just, they used to be like this and they've been tilted on their sides like this. In other words, they've been totally squashed and folded. Remember the folds you learned about anticlines, synclines, and monoclines? These are radical, what we call complex folds, where most of them are big giant anticlines that have folded shut. They're really impressive. This is a clue that told you how they were formed. This is a fault-blocked mountain range. And you see all these features, you can start to interpret what you're seeing in person better. It also makes you aware that these areas are prone to things that could be geologic hazards, which you'll learn about in the next lecture. I'm going to leave you with this thought right here. This is a slot canyon. I mentioned it earlier for Antelope Canyon, but I want to show you what it looks like as you're going into the canyon and what it looks like in it. It's just a crack at the surface like this. Now, sure, yeah, you could fall in respectively at night, I guess, if you didn't know it was there, and I'm sure that's happened, but it doesn't look that impressive. My point is that sometimes you got to get to where these things are, hike down into them, hike up to them. You've got to see the rest of the picture. Oftentimes in science, that means we got to get up in the air and we got to look down. In this case, we had to get down into it to really see what was going on. If I saw a crack like this and I was out in the desert, I would always pay attention, because while it's dry and arid out there, all you need is a half an inch of rain upstream somewhere, and you could flash flood this place and be in real trouble. And that has happened to a series of people in these locations. So I just want to encourage you to look at the clues around you. Think about not just the science of what you've learned, but how does it apply to you and your life? If you know that, then the course has a relationship to you. It actually brings and bears some kind of meaning to where you might be if you went and traveled ever, or you decide to move to a location like this. Page, Arizona is very remote, and it's the site of one of two dams in and along the Colorado River. One is Hoover Dam right by Las Vegas. The other one is in Lake Powell, and it is why this area has a city in Page, Glen Canyon Dam. And both of them represent areas of the Colorado Plateau, or the Colorado River specifically, that got dammed up. I'm not seeing these slot canyons form by damming up the river. I'm not making that correlation at all, but I'm telling you flash flooding did cause them. There's more slot canyons out and around areas of the world, but they all have a common theme, and they all should be, while they're beautiful, just be careful and know your surroundings.
Welcome to Crater Lake National Park. Crater Lake is located in Oregon, and the big question is, why does it look the way it does? Crater Lake is the result of ancient volcanic eruptions that actually had such power that they blew out a lot of magma, lava, very, very quickly, creating a caldera, which is a very special geologic feature where the volcano collapses inside of itself. The eruption that caused this occurred approximately 7,700 years ago, but has evidence now of recent volcanism in the form of the volcano that was just indicated to you. That volcano is Wizard Island and represents resurgent caldera activity. Whenever you see that, that should send a flag up. Notice the light-colored igneous rock. That's very, very characteristic of any subduction zone around the world, because you got blending of basaltic and felsic crust at a subduction zone. When you look at Wizard Island, it shows evidence of very recent eruptions, even the lava that's capping the flows at the top there, that should be very indicative of a dangerous situation anytime you see resurgent activity growing inside the floor of a caldera. So, all calderas basically have the same shape. They're circular. When you get this zoomed out view, panoramic view of Crater Lake, you'll begin to see there's a big gigantic rim. You need to imagine that magma chamber collapsed inside of itself. And that's why these basically have the same shape around the world. Not all calderas are filled with water like Crater Lake, but all calderas represent ancient volcanic eruptions. So the next time you see one, you'll know how it formed. This is truly a volcanic legacy. See you at the next stop. Bye.
As I leave you, I will say, now that you've seen how Crater Lake forms, you know what it is. Would you recognize a caldera if you saw it elsewhere? I think the answer might be yes. If you saw a slot canyon somewhere, would you know how it formed from flash flooding? Would you recognize at least the basic three body plans of volcanoes? Can you at least see how mountains vary and why mountains are different from things like hills? How we have plains versus other landforms like mesas and buttes and hoodoos and arches. These are all landscapes that you will likely come in contact some, I hope some, in your lifetime as you get out to see this marvelous planet we call Earth. Thank you so much for your time. I'll see you at the next stop. Bye.